Right, good evening, everyone. Hope you're all well, and hope you're all excited about getting back to school or college. Last one of these, given that the schools are all back on Monday, so hopefully it's helped you keep going through the lockdown. So what I'm going to do today, as promised, is binomial hypothesis tests, but now looking at two-tailed tests and critical regions. So let's give an example of a two-tailed test. So this one here, a coin is tossed 20 times. I should have done my sound check, shouldn't I? Type something in the chat if you can hear me. Anything at all. Nice one, brilliant. Zamster, Christine, good to see you both again. The regulars. So a coin is tossed 20 times and lands on heads 6 times. Use a two-tailed test with a 5% significance level to determine whether there is sufficient evidence to conclude that the coin is biased. So the coin being biased, so last week what we did, it told us which direction it tested. It told us whether the probability of a head was more than 0.5 or less than 0.5. The coin being biased in this case means that P could be bigger than 0.5 or P could be smaller than 0.5. In fact, that means just P not equal to 0.5. So we don't know whether to test for a greater than or less than. That's what makes it a two-tailed test. So in essence, we're going to test for both of those things. So when that happens, first thing, define in words what P is. So P equals the probability of a coin landing on heads and the null hypothesis, if we trust the coin to be real and fair, would be the probability of it landing ahead is 0.5. And the alternative, we can't say whether it's greater than or less than 0.5. We're just being asked whether it's biased. So it's P is not equal to 0.5. So this here is what makes it a two-tailed test. H1 of this form makes it a two-tailed test. Feel free to ask any questions along the way. So the coin's tossed 20 times and it lands on heads 6 times. Our observation is 6. So our observed value, I'm writing it in red because this won't form part of the answer, equals 6. And we've got to decide whether that's more or less than expectation. Which for XB, and there's 20 coin tosses, probability, if all is well with the coin, of 0.5. How many heads would we expect if we toss this fair coin with a probability of a half 20 times? I've asked to define a two-tailed test and give an example in an exam. You're certainly expected in exams to do two-tailed tests. So to understand this, it is necessary. If that answers your question as a hamster. So my question to you all, though, with a fake coin that we toss 20 times, how many heads do we expect? Ten, yeah. So 20, and half of them are going to be heads. So we expect 20 times 0.5 equals 10 heads. Therefore, 6 is a decrease from expectation. So everything I'm writing in red here, you're not necessarily expected to write down in an exam, but you are expected to understand it and be able to do this thought process. Yep, Laura, I see yours now. 10 was correct. So now we're going to test the left tail. It's a decrease. Therefore, test only left tail. So we're finding the probability now that x is less than or equal to 6, testing for a decrease. And here's the twist with a two-tail test. So you saw my probability diagram last week, where if we were testing to the left, we reject the bottom however many percent, and we're testing to the right. Try that again. And if we're testing to the right, we test the top 10%, or whatever the significance level was, in this case 5%. When it's a two-tail test, we split the significance level equally between the two tails. So instead of 5% now, we're putting 2.5% in each tail. So the reason for that is, if we're working for a drugs company, say, and we're designing an experiment, if we have no idea which way the test's going to go, whether it's going to go right or left, we have to set out our experiment months in advance before we start doing the testing. So it almost seems to make no sense that now that we know it's decreased, that we're testing both tails, that we're testing an increased tail and a decreased tail, splitting the significance level between the two. But I'm afraid that's how the experiment was designed, to go backwards and change our hypothesis after we've got the evidence. Sort of seems unethical. It's almost like cheating in a test, changing your answer after you've seen the mark scheme. So once we've committed to this test, testing 2.5% each side, i.e. a two-tail test of 5%, then we stick with it. So now the probability that x is less than or equal to 6. So let's go to the binomial distribution, binomial cumulative distribution, and the probability that x is less than or equal to 6. There were 20 trials and probability of 0.5 of getting ahead. That makes it 0.05766. Right, so you might think to yourself, well, actually, why don't we do a greater than or equal to as well to test the right-hand tail? Well, if the evidence is that it's decreased from expectation, there's no real point in testing the right-hand tail. We know it's not going to show an increase because the data has shown a decrease. We can use common sense to disregard the right-hand tail. The only one relevant really is the left-hand tail. The only one we've got hope of rejecting the null hypothesis for is the one in which the data has gone in the same direction. There is no way we could convince anybody that actually there are more heads coming up than usual and present them with the evidence 6 when you actually expected 10. So we can just dismiss that outright. We've seen a decrease. There's no way that that's going to show evidence of an increase. So we'll just not bother testing it. So now 0.05766 is bigger than our significance level on the left-hand tail, which is 0.025. So to the left of 6 lies 5.766% probability. So roughly 6 lies there with 5.766% of probability to the left of it, i.e. outside of our rejection region, or the critical region, as it's also known, as we're about to discover. Therefore, do not reject H0. Insufficient evidence to suggest that. And let's go back to what the question said. The coin is biased was our initial hypothesis, so that's what we refer to in the conclusion, that the coin is biased. So here's a past exam question. I'm going to give you a few minutes to try that. 7 marks. I need you to do basically exactly the same things, incorporate in your answer, exactly the same things that I did above, so I'll leave that all on the screen. So take a few minutes to do that. I'll come in about 5 minutes. So I'll get you started a little bit. So the manufacturers of a brand of chocolates claim that on average 30% of their chocolates have hard centres. In a random sample of 8 chocolates from this manufacturer, 5 had hard centres. Test at the 5% significance level where there is evidence that the population proportion of chocolates with hard centres is not 30%, stating your hypotheses clearly. Show the values of any relevant probabilities. In this case, our P is going to represent probability that a chocolate has a hard center. Now, null hypothesis. Well, the manufacturer claims 30%. However, that's disputed and doesn't tell us whether it's more than or less than 30%, just that it's not 30%. So there's your first 2 marks for those 3 statements. And our observed data was 5 had hard centers. So the binomial distribution we're going to use, there were 8 chocolates, and we're testing the assumption that it's 30% or 0.3. So how many chocolates are we expecting to see with hard centers? And I'm happy to accept a decimal answer. The answer will be decimal. Type it in the chat. How many chocolates were we expecting to see have hard centers? Yes, Laura, correct. Well done. 2.4. Because 8 times 30% of the chocolates have hard centers indeed means we expect to see 2.4 with hard centers. That means having observed 5, that's an increase. So 5 certainly is greater than what we expected. So testing for an increase. So now, the probability that x is bigger than or equal to what we observed, 5, equals 1 minus the probability that it's less than or equal to 4. Our calculator needs to be able to do it. So 4 in the calculator. Number of chocolates was 8, and the probability of winning, i.e. getting a hard center, is that there. So equals 1 minus, and that number was 0.9420. Which if I go to ordinary calculation mode, 1 minus answer gives us 0.05797. Remember though, we have to split our significance level between both tails in order to get the marks. And everything I've written in blue is required to get the marks. So 5% significance level, that's 2.5% on each side. And remember, we discarded that one. We found an increase, so there's no point in testing for the left-hand tail. The fact it's increased has told us that hasn't happened. And now just do our comparisons and conclusions. 0.05797 is bigger than 0.025. Needs to be 0.025 to get a mark. Do not reject H0. Insufficient evidence. To suggest that the proportion of chocolates with hard centres is not 0.3 or is not 30%. So that's how to do two-tailed tests. So what we're going to look at now is the idea of a critical region in a hypothesis test. So having been able to do one-tail and two-tail tests, the final piece of the puzzle is critical region. So critical regions of hypothesis tests. And this here, I'll define what it is to be a critical region first of all. So a critical region, abbreviated CR, is the set of all observed values of x that would lead to the null hypothesis being rejected. The set of all observations that would lead to the null hypothesis being rejected. So let's have a look. I'll bring an example up. So let's take this example here. There's no context to it. It says p is not equal to 0.22. I'm going to change that slightly since it's our first example to make it a bit easier. I'm going to say p is less than 0.22 to make it a bit easier. So a random variable has distribution binomial 10p. A single observation is used to test the null hypothesis p equal to 0.22 against the alternate hypothesis p is less than 0.22. So my question is, find the critical region at the 5% significance level. So we're looking, first of all, at the left-hand tail. We can see that's a less than, so we know we're going to reject on the left-hand side. So if I'm doing this rather crude diagram here, I want to find out exactly what observations, what values of x would lie in that region there. So what I'm going to do, get the calculator now, and this is a mode you probably haven't used before. Distribution, binomial cumulative, but we're going to use the list function. And we're going to look at all the different possibilities that there could be. So 0, 1, 2, 3, 4, 5, 6, 7, 8. So I'm telling the calculator I want it to calculate for me all at the same time to put in a nice table the probability that x is less than or equal to 0, probability that x is less than or equal to 1, 2, 3, 4, 5, 6, 7, 8. So keep going until I get bored. So there were 10 observations, and the probability of winning was 0.22. So there we have it there. So if I show you what the calculator has given us. So this is an interesting output because we can see the probability that x is less than or equal to 0 is 8.33%. The probability that x is less than or equal to 1 is 31.84%. So actually, none of these observations at all lie in our critical region. If the test had have been, say, 10%, then actually we could say that x equals 0 would lead to a rejection because 8.33% is less than 10%. If I'd have said, if we did a particularly rubbish test, let's say 70% significance level, you never would do that. That's a ridiculous thing to do. But if you were to do a 70% significance level, the critical region would be 0, 1 and 2, because all of those probabilities lie below 70%. They would be rejected. So let's try another, now that you've got your head round how to do these, and hopefully this one will work. So a random variable has a distribution binomial, 20p. A single observation is used to test the null hypothesis, p equals 0.15, against the alternate hypothesis, p is less than 0.15. Using a 5% significance level, find the critical region of the test. So do exactly what I just did. Get your calculator, and it's another test for the left-hand tail. So use your calculator to calculate a load of less than or equal to values. And just see which one lies below, which ones lie below 5%. So take a moment to do that. I will do it myself in just a little while. So on your calculator, the inverse binomial button, I've found that it can be quite unpredictable at times. So are you talking about on the graphical calculator, Laura? Yeah, so I found it quite, it behaves quite strangely, that function, and sometimes it gives me the number above or the number below, and I haven't quite been able to figure out why, but I'm willing to be educated on why that is, because I haven't really committed enough time to investigating why. I probably should do that, actually. So for now, I would say it's better to show you working this way. And I'll show you the points, the points that they need for working on an exam in just a moment. So I'll go through and show you exactly what you need to write down to get the marks on these when it asks you to find the critical region. But drop me an email about it, and I will investigate. So you go to my website, it's on there. So drop me an email and I'll have a look more deeply into it. Right, so we're trying to find the critical region of the test. So it's given us the hypotheses. So I've already got in from last time that I want to find 0, 1, 2, 3, 4, 5, 6, 7, 8. By 8 I've got a bit bored. And this time there were 20 observations. 0.15. So I'm just hoping 8's going to be enough. If it's not enough, then I'll put more in a bit. And there's the table there. So I can see here that 0 is going to be rejected. That's less than 5%. But that's all. As soon as I get to x less than or equal to 1, I'm up to 17.55%. So what I'd write down to get the marks, the probability that x is less than or equal to 0, which is also in binomial, the probability that x is equal to 0, equals 0. And best hover over it because it truncates rather than rounds. So actually it looked like it was 0.0387, but actually it's 0.0388. Given the next number, equals 0.0388, which is less than 0.05, which would be a reject. Probability that x is less than or equal to 1 equals 0.176, which is greater than 0.05, which is a do not reject. Therefore, we've seen it crossing the threshold from do not reject to reject, or vice versa, from reject to do not reject. Therefore, we've shown the true size of the critical region. Therefore, critical region is x equal to 0, and that's it. Technically, I could write x less than or equal to 0 and get away with it as well, because it only goes down to 0. But the only observation that would lead you to rejection would be x equals 0. And hopefully to answer your question, Laura, so I'm 99% sure. So all the mark schemes I've seen require you to show the last reject and the first do not reject. And using the inverse binomial function wouldn't do that. It might get you to the answer, it might get you the numbers you need to test quicker. But in order to get the marks from all the mark schemes I've seen, you might be able to show me a new one where that isn't the case. But showing it crossing the threshold like that is necessary. So you've got to pander to what the exam boards want. So we've only tested left-hand tails now, which are relatively straightforward, as you can see. Let's do a right tail test and find the critical region for a right tail. So a random variable has a distribution 20p again, and a single observation is used to test h0. So I've just copied the exact same one down, haven't I? Give me a moment. It was this one that I wanted to do. So a test statistic has a distribution 10p. Given that the null hypothesis is 0.2 and that the alternate hypothesis is p is greater than 0.2, find the critical region for the test using a 5% significance level. So I'm about to tell you the theory behind why I'm about to do what I'm about to do here. So we want the probability such that x is greater than or equal to a particular number, because we're testing to the right, so the right hand tail, to be less than the significance level, less than 0.05. But unfortunately our calculator only does less than or equal to. So what we're actually looking for is the probability that x being less than or equal to n minus 1 is greater than 0.95. What I've done, I've swapped the n with, I've flipped the inequality, turned that into n minus 1 and done 1 minus. Change that n minus 1, flip the inequality, did 1 minus, and that inequality's changed as well. And I'm just going to show you what I've done there mathematically. So, the probability that x is greater than or equal to n is identical to 1 minus the probability that x is less than or equal to n minus 1 is less than 0.05. So that there is identical to that. I'm going to take 1 from both sides now to give minus probability x is less than or equal to n minus 1 is less than, and take 1 from that, we get minus 0.95. Then times both sides by minus 1 to get the probability that x is less than or equal to n minus 1. Flip the inequality because we multiply by a negative number is greater than 0.95. So hopefully I've proved why that's the case. Flip all the inequalities, replace it with n minus 1, 1 minus. So it's a rule to remember, to go straight from there to there. However, this proves it. So now in our calculator, and we're testing the right hand tail. So it makes sense now to start at the upper end. So we started from 0 when testing the left hand tail. I think it makes sense now to start from the right hand tail, 10. So 10, 9, 8, 7, 6, 5, 4. Probably done enough. If I haven't, I'll do more later. 10. And the probability we're testing is 0.2. And we're looking for it to go below 0.95. So we want all the ones above 0.95. So we want to see the threshold being crossed. So there we have it there. So if I take a snapshot of that, make it bigger. So the region, we can see there. So if my n minus 1, which is this bit here, equals 4, this implies that the probability is 0.9672. And let's just check, let's do it with 3 decimal places, 0.967. And that's clearly bigger than 0.95. When our n minus 1 value equals the next one down equals 3, that means that p equals 0.879, and we've crossed the threshold. So we've gone from reject to do not reject. Therefore, n minus 1 equals 5. N minus 1 equals 4. So n equals 5. So any observations now greater than or equal to 5 will be rejected. The critical region is x bigger than or equal to 5. Let's do a practical example of that. Okay, so seedlings come in trays of 36. On average, 12 seedlings survive to be planted on. A gardener decides to use a new fertiliser on the seedlings, which she believes will improve. So already we're being told the direction of the test will improve the number that survive. It's not a two-tailed test, we're being told we're testing for an improvement. Describe the test statistic. Well, that's us writing in words what we're testing, P. So P is the probability a seedling will survive probability that a seedling will survive. The null hypothesis well, 12 out of 36. On average, 12 seedlings survive to be planted on in the tray of 36. So the null hypothesis is 12 out of 36. P equals a third. And the alternate hypothesis, well, we think it's improved now. So if they're right, P is going to be bigger than a third. So I've done part A. So part B, using a 10% significance level, find the critical region for a test to check her belief. Well, we're testing the right hand side, so we want the probability that x is bigger than or equal to a number to be less than the significance level. Now we have to mess around with that a bit because our calculator doesn't do greater than or equal to, unless I'm assuming you've got the CG50, Laura. If you want to do some greater than or equal to probabilities in that, that's fine. If you come to the same conclusion, you can just prove that inequality there. The reason I'm doing it this way is because the standard calculator won't handle that. So if you want to show it crossing the threshold with your calculator using that, that's fine. But for those of us with standard calculators, okay. Drop me an email and I'll send you some instructions, okay? So we want the probability that x is less than or equal to n minus 1 to be greater than 0.95. So, seedlings come in trays of 36. 36, 35, 34, 33, 32, 31, 30, 29, 28, 27. Probably done enough. If I haven't, I'll put more in later. So the number was 36, and 1/3, 1 divided by 3, was the probability. So I'm looking for a crossing the boundary over 0.95. So it looks like I haven't done enough. So let's continue. 27, 26, 25, 24, 23, 22, 21, 20. Still nowhere near. So 19, 18, 17, 16, 15, 14, 13, 12, 11, 10. We'll get there. It doesn't take that long. A minute at most we've wasted by putting all these probabilities in. And there we go. There it is there. Now there are ways of speeding it up, but when I'm introducing this topic, I don't want to add too many different things in. So I'm going from very basics at the minute. It might take a bit longer, but it's certainly the easiest way for now. So n minus 1 equals 17. Means that p equals 0.972, which is greater than 0.95. n minus 1 equals 16. Means that p equals 0.942, which is less than 0.95. We've shown it crossing over the threshold. So we've got n minus 1 equals 17, which means that n must be 18. Therefore, the critical region, any observation above 18 will be rejected. One more example, and this time we're going to do it for a two-tailed test. Finally, for a two-tailed test, a random variable has distribution, binomial 20p. A single observation is used to test the null hypothesis 0.4 against the alternate hypothesis of p not being 0.4. Using the 5% level of significance, find the critical region of this test. Well, there's going to be two potentially critical regions. We've got to look for one to the left and one to the right. So 5% level of significance, 2.5% will be on the left and 2.5% will be on the right. So let's do the left-hand tail first. So the easy one. So there's 20 things. So if we're doing the left-hand tail, we should start low. Start with the left-hand numbers. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the number was 20, and the probability of success was 0.4. So we're looking for it going over 2.5%, and we can see there it happens. So showing you here, we can see that it goes from rejection to non-rejection between 3 and 4. So just writing that down, x equals 3 means the probability equals 0.016, which is less than 0.025 when x is 4. P equals 0.0509, which is greater than. I'm glad you're finding it useful. I'm really glad you find it useful. Thank you for the nice comment. Which is greater than 0.025. Therefore, the left-hand critical region is x less than or equal to 3. anything 3 or less will lead to a rejection. Now let's do the right tail. So we want the probability x being bigger than or equal to a value to be less than 0.025. And working all the magic we did before, we can see an equivalent statement, the probability that x is less than or equal to n minus 1 being bigger than 0.1 minus that, 975. And as I say, we proved earlier why that was the case. So let's start from let's go back and start high. This time we're testing the right tail, so we start from 20. Because there were 20 observations, 19, 18, 17, 16, 15, 14, 13, 12, 11, 10. Let's hope that that's enough. And let's look for a crossing the 0.975 boundary. If we don't see that yet, I have seen it. So there it is there. So in this case, n minus 1 equaling 12 gives us probability equal to 0.979, which is greater than 0.975. That's what we wanted. N minus 1 equals 11 gives us p equals 0.943, which is less than 0.975. Therefore, n minus 1 equals 12, which means that n equals 13. So the critical region is all observations greater than or equal to 13 would lead to rejections. Therefore, the overall critical region is the set of all x's such that x is less than or equal to 3 or united with the set of all the x's such that x is greater than or equal to 13. Both those sets united would lead to rejections. So we've got two separate critical regions that we would reject at the end. Yeah, I'll have a think about the calculator skills. That sounds reasonable. Yeah, I'll have a I'll try and put a bit of time to one side. Yeah, reasonable request, no problem. So there's the critical region. Let's have a look back at the question. Write down the actual significance level of the test. Right, so the actual significance level is the size of the rejection region in terms of probability. So part B, answering part B, it's the probability that x is less than or equal to 3 plus the probability x is greater than or equal to 13 the size of the rejection region. So let's work that out. Well, we know the probability that x is less than or equal to 3. It was 0.016, but I didn't save that number, so I best get it back up to be safe. So put in the non table mode. So x is less than or equal to 3. No 0.01596. and then plus 1 minus the probability x is less than or equal to 12. I'd have to check the specification for whether it applies to CIE. So I would assume if CIE do hypothesis testing, I would assume if CIE do hypothesis testing that this will be on there, yes. So less than or equal to 12. So equals 0.01596 plus 1 minus that, 0.9790. So 0.01596 plus 1 minus our answer previously equals 0.0370. Is the actual significance level of the test. We wanted the significance level to be 5%. But unfortunately, by the nature of the binomial distribution, we could only manage 0.0370, 3.7%. So we set off with a significance level we want, but because the binomial distribution works in blocks of probability, every time you add a number in, you add an extra block of probability in there, we're never going to get exactly 5%. And that's the difference between actual and desired significance level. So that's it. I'm back to work on in person on Monday. You will all be back to school and college. So very much hoping that this has been useful. And yeah, check out my website, alevelmathsrevision.com. Plenty free on there for you to look at. Loads of exercises. Practice this. So I might do one of these in future. When I get time. But for now, and you asked if it's for Edexcel, it's for any of the UK A-level exam boards. And you'd have to check your own specification. And check whether this is on. I wouldn't be able to tell you off the top of my head whether it's CIE. If it is on CIE, it'll be in obviously the stats module. Edexcel IL. Just Google the specification. Check for binomial hypothesis testing on it. So I'm not 100% off the top of my head sure of all the syllabuses, unfortunately. But drop me an email. I can find out for you. So I'm glad you found it useful. Have a good rest of the evening and hope all goes well getting back to school and college.